What specific problem does ULTRAIF aim to solve in the context of instruction following data synthesis for large language models?
ULTRAIF aims to solve the problem of generating high-quality instruction following data for large language models, LLMs, by addressing the limitations of existing methods that either rely heavily on human annotators or solely on LLMs' instruction-evolving capabilities. The current approaches face challenges in scalability, cost efficiency, and the diversity of instructions, often resulting in low-quality samples. ULTRAIF introduces a two-stage process that decomposes real-world user instructions into simplified components and constraints, while also generating evaluation questions to verify the correctness of responses. This method allows for the synthesis of diverse and complex instructions, enhancing the instruction-following capabilities of LLMs without the rigidity and homogeneity introduced by handcrafted constraints. Ultimately, ULTRAIF significantly improves the scalability and quality of instruction following datasets, making it a more effective solution for training LLMs.
How does the proposed ULTRAIF method work? Illustrate the process step by step, focusing on the ULTRAComposer and the Generate Then Evaluate framework.
The proposed ULTRAIF method operates through a two-stage process involving the ULTRAComposer and the Generate Then Evaluate framework. First, the ULTRAComposer is constructed by decomposing real-world user instructions into simplified components and constraints, along with generating corresponding evaluation questions. This decomposition allows for the synthesis of diverse and complex instructions, while ensuring that the generated responses can be verified against the evaluation questions. In the Generate Then Evaluate framework, the ULTRAComposer takes the simplified instructions and incorporates the constraints, generating augmented instructions. Subsequently, the model prompts LLMs to produce multiple responses for each instruction, which are then evaluated against the generated questions to assess their quality. This iterative process not only enhances the complexity of the instructions, but also ensures the correctness and reliability of the responses, ultimately leading to the creation of a high-quality instruction-following dataset.
Can you provide a simple example demonstrating how ULTRAIF decomposes a user instruction and generates an evaluation question? Please walk through the example with all relevant components.
Certainly. For instance, consider the user instruction. In Shakespeare's tone, recommend me 10 Chinese books. ULTRAIF decomposes this instruction into two components. A simplified instruction, X_1, which is recommend me 10 Chinese books, and a constraint, C_1, which is in Shakespeare's tone. Following this, ULTRAIF generates an evaluation question, Q_1, to verify the response's adherence to the constraint, which would be, is the response written in Shakespeare's tone? This structured decomposition allows ULTRAIF to create a clear framework for generating diverse and complex instructions, while ensuring the correctness of the responses through the evaluation question. Thus, the process effectively transforms a complex user request into manageable parts that can be systematically addressed.
What are the theoretical or practical benefits of implementing ULTRAIF compared to previous methods in terms of cost, efficiency, and instruction diversity?
The implementation of ULTRAIF offers significant theoretical and practical benefits over previous methods, particularly in cost, efficiency, and instruction diversity. Firstly, ULTRAIF reduces costs by a factor of 3 to 5 compared to methods like AutoIF, as it achieves high-quality instruction synthesis with only 3 to 4 calls to the LLM, minimizing computational expenses. Secondly, the Generate Then Evaluate process enhances efficiency by streamlining the generation and evaluation of responses, eliminating the need for separate score filtering stages, which further accelerates the data generation process. Lastly, ULTRAIF excels in instruction diversity by utilizing the ULTRAComposer to decompose real-world user instructions into simplified components and constraints, allowing for the synthesis of complex instructions that better reflect varied user needs, unlike previous methods that often led to homogeneous outputs. This combination of cost-effectiveness, efficiency, and enhanced diversity positions ULTRAIF as a superior approach in the landscape of instruction following data generation.
How was ULTRAIF validated in the experiments? Discuss the datasets, metrics, and benchmarks used to test its performance and the outcomes of these evaluations.
ULTRAIF was validated through comprehensive experiments on 5 instruction-following benchmarks: IFEval, MultiIF, InfoBench, FollowBench, and LiveBench. These benchmarks were chosen to assess ULTRAIF's performance on both verifiable instructions and more general instructions requiring LLM evaluation. The evaluation metrics included precision scores, PRS, and instruction scores, INS-S, with ULTRAIF achieving notable improvements over existing methods, such as scoring 53, 97 PRS, and 64, 15 INS-S, on IFEval, surpassing the baseline auto-IF by margins of 1.29% to 6.84%. Additionally, ULTRAIF demonstrated strong performance across various domains, including mathematical reasoning, coding, and conversational tasks, with significant improvements in LiveBench and ArenaHard benchmarks, indicating its versatility and effectiveness in handling diverse instructions. Overall, the evaluations confirmed ULTRAIF's capability to enhance instruction-following abilities while maintaining high scalability and cost efficiency.
What limitations does ULTRAIF have, particularly regarding its scalability or the complexity of instructions it can handle effectively?
ULTRAIF faces limitations in scalability and the complexity of instructions it can handle effectively due to its reliance on the UltraComposer model, which, while designed to synthesize diverse instructions, may still encounter challenges with overly complex or nuanced instructions. The handcrafted constraints introduced to guide the instruction generation process can lead to rigidity, resulting in homogeneous instructions that may not fully capture the diversity of real-world user requests. Additionally, while ULTRAIF aims to enhance instruction complexity, there is a risk that as instruction complexity increases, the performance may not scale linearly, potentially leading to diminishing returns in instruction-following capabilities. The iterative augmentation process, although beneficial, can also introduce performance degradation if the optimization objectives shift unfavorably during training. Lastly, the need for evaluation questions to ensure response quality may limit the speed and efficiency of generating large-scale datasets, as it requires additional processing to assess the generated responses against these questions.